Good morning, everyone. I'm going to discuss finding the zeros of polynomial function. So when we say zeros of polynomial function, when we say zeros, so this is the same with the roots of a polynomial function, the solutions of a polynomial function. Now, the zeros of polynomial function or finding the zeros of polynomial function will help us sketch the graph of a polynomial function, which is what I'm going to discuss next meeting. Now, before we proceed with working on the zeros of polynomial function, it's necessary that we have to recall some factoring formulas that you have learned in your previous mathematics classes. So we have working on the common monomial factor. So this is just done by identifying what is the common, or should I say greatest common factor among the terms, like among these three terms. So in this case, the common factor is A. So we divide both terms by the common factor. So that resulted to the second factor. And that is how we work on the common monomial factor. Another one is the difference of two squares. So we are talking of two terms here. So we're working on binomial with subtraction operation, and both terms here are perfect squares. So the difference of two squares is obtained by extracting the square root of both perfect squares here. Like we know that the square root of a squared is a, while the square root of b squared is b, because extracting the square root of an expression will just require us to divide the exponent by 2. So we get a here and b here. Now, these a and b will serve as the terms of the binomial. If one is addition, the other factor should be subtraction or vice versa. So we have a plus b quantity a minus b as the factors. For a perfect square trinomial, we have to we are actually factoring a perfect square trinomial. How do we describe a perfect square trinomial? So the first and the last terms are perfect squares. We know that perfect square expressions are expressions when raised to the second power. For example, 1 squared, 2 squared, 3 squared, and 4 squared are perfect square expressions, meaning 1, 4, 9, and 16 are perfect square expressions. In a case of algebraic expressions, variables raised to the second are exponents of variables which are even are considered as perfect square. So m squared n to the fourth are perfect. This expression is perfect square. Like 25 a to the fourth is a perfect square expression. 100 y to the 16th is a perfect square expression. We know that 100 is a perfect square, while 16 is even. So we can say that 100 y to the 16th is a perfect square expression. Now, both terms of trinomial must be perfect square. And then as we extract the square root of those perfect square expressions like a squared and b squared, we know again that the square root is a and b. And then as we multiply the extracted square root of the perfect squares, and then we double that, it has to be the middle term. So a times b and then times 2 is the middle term. So in that case, we can describe the left side of the equation here as perfect square trinomial. And the factors are two same binomial. So this can be associated with square binomial and special product. So the factors are the extracted square root, and we separate them by either a plus sign or a minus sign, depending on the sign of the middle term. Okay, so the factors are a plus minus b quantity squared. For the sum and difference of two cubes here, so we are working on binomial again. This time, the operation is either sum or difference, addition or subtraction, and both terms here are perfect cube expressions. Now, perfect cube expressions, on the other hand, are expressions when raised to the third power. like if we raise 1 to the third, 2 to the third, 3 to the third, and 4 to the third, the result is a perfect cube expression. And the right side of each of these equations is a perfect cube expressions. With algebraic expression, so the requirement is the exponent must be divisible by 3. So we have m cubed n to the 6. So this is perfect cube expression. And then b to the 27 is a perfect cube expression. 125 m to the 6 is a perfect cube expression because it satisfies the definition of a perfect cube expression. Now we will try to factor each of these polynomial, and then we're gonna make use of these factoring formulas. So 10x to the fourth minus 160. We know that both terms have common factor. Maybe we can work on the GCF first, move out the GCF, and the GCF is 10. And then we'll divide both terms here by the GCF 10. So as we divide 10x to the fourth by 10, we have x to the fourth. And then negative 160 by 10, we have negative 16. After doing so, these are the factors, but these are not the complete factors because obviously the second factor here has or is still factorable, and this is the difference of two squares. So for the difference of two squares, again, we'll work on the square root of both terms here. So we'll extract the square root of x to the fourth, so that's x squared. And then we'll extract the square root of 16, so that's 4. So these are the factors, including the GCF. But again, this is still factorable. And the factors, since this is the difference of two squares, again, we'll extract the square root of both terms. So we have x and x here. And then, no, this has to be 4. Okay, square root of 4 is 2. So this is plus and then minus. So the final factors are, we have the GCF and then this, and then x plus 2, x minus 2. So these are the complete factors. Okay. For x to the 6 minus 4096, so 4096 is a huge number, but I'm telling you 4096 is a perfect square expression as well as x to the 6. So again, we can work on the difference of two squares. So as we extract the square root, so we have these factors. We're going to consider this one, no? So we have square root of x to the 6 is x cubed. Well, square root of 4096 is 64. So this is x cubed plus 64 and then x cubed minus 64. But then again, both factors here are still factorable. In fact, this is the sum of two cubes. Well, this is the difference of two cubes. So we will follow the last two formulas here. So we're going to extract the cube root of both terms. So let's work on this and place the answer here. So we have square root of x cubed is x, while square root of 64 is 4. And then we'll work on the second factor. So we'll square x and then multiply the 2 times negative 1. That's why this is plus, then the middle term is a minus sign. This is minus, then the middle term is a plus sign. And then it has to be the square. For the factor of the difference of two cubes here, we'll work on the cube roots again. So this is x minus 4. And then the trinomial factor, first term is the square of x here. And then the product of the two terms times negative 1. So this is plus 4x this time. And then square of negative 4. So let me just arrange the factors. Like I'd like to write first the binomial factors. X plus 4, x minus 4. And then the two trinomial factors, x squared minus 4x plus 16, x squared plus 4x plus 16. And these are, these are the complete factors. Number 3 class is a perfect square trinomial. Both terms here are perfect square, and the square root of 1 to 1 x squared and 25 equals 11x and 5 respectively. And then as we work on the product of 11x and 5, we multiply this by 2. This is equal to the middle term, 110x. So really, number 3 is a perfect square trinomial. And the factors are the extracted square root. So we separate them by a plus sign since the middle term is addition. And then plus 5 quantity squared. So these are the factors. Why we recall factoring? Because factoring can be an easy step for us to work on the zeros of polynomial functions. Here, how do we find the zeros of a polynomial function? One can be done by factoring. The other one can be done by working on either of this theorem that I have discussed. So we can work on the remainder theorem or the factor theorem. Okay. So if we're going to consider like working on f sub 1, and if it turned out to be 0, then 1 is the remainder. No, so meaning x minus 1 is a factor of this polynomial function. So that's how we interpret it. Okay, so we are now working on the zeros. So if we have 1 cube here minus 6 times 1 squared plus 11 times 1 minus 6. Now this is 1 and then minus 6. So we have negative 5 minus 6. We have negative 11 plus 11. So definitely this is equal to 0. Now if that's the case, then we can do synthetic division. 1, negative 6, 11, negative 6. And let's make use of 1 as the 0 for us to identify the other zeros of this polynomial function. So it's confirmed that 1 is one of the zeros. Now, as we do division and we divide the polynomial function by x minus 1, so this is how it works using synthetic division, no, as what I've discussed to you. So we'll bring down 1 times 1. So everything is addition here. So 1 plus negative 6 is negative 5 times 1. So we have negative 5 plus 11. We have 6 here. Oh my, wait. So this is 6 times 1. So we have 6. That's why this is 0, no? Because x minus 1 is one of the factors. Now, the result is x squared minus 5x plus 6. We can do factoring as we work on the zeros. Like, it's a perfect square trinomial. We have x and x. And then the factors of 6 are negative 2 and negative 3. As we add the 2, it matches with the middle term. So minus 2, minus 3. So if the factors are x minus 2 and x minus 3, we'll just equate each of the factors to 0. So we'll come up with the root x equals 2 here and x equals 3. So therefore, the roots, or I mean the zeros, equals 1, 2, 3. Now, we tried working on f of 1, and that equals 0. We also expect that f of 2 equals 0, as well as f of 3 equals 0. Okay? Now, for number 2, we're going to work on the zeros again. We will, since the common factor for each term here is x, so we'll just divide this function by x. So we get x cubed and then 5x squared plus 2x minus 8. If one of the factors if one of the factors is x, then one of the zeros is 0, x equals 0. Now, very obviously, when you substitute 0 to all x here, then it will result to 0. If each term here is multiplied by 0, of course, we expect a value of 0. So f of 0 equals 0. So meaning 0 is one of the zeros. So the remaining expression will make use of synthetic division, like we can make use of 1 as a possible 0. And later you will know why we are using 1. In the next slide, I'll be introducing a theorem, and you will know why we use 1 as an option for a possible 0. So we'll bring down 1 here times 1, and we are using synthetic division again. And then plus 5. So we have 6 times 1, 6 plus 2, 8 times 1. Okay, it's 8. So we come up with 0. So meaning 1 is possible 0. So we have the remaining expression x squared plus 6x plus 8. So we will do factoring for us to find another zeros, no? So x here, so 8. So the possible factors of 8, which result to the sum of 6, is 2 and 4. So if these are the factors of this, then x plus 2 equals 0, as well as x plus 4 equals 0. So we have x equals negative 2, and then x equals negative 4. So the zeros of these polynomial functions equals 0, 1, negative 2, and negative 4. So one way of working or identifying the possible rational zero of a polynomial function is done by working on the rational root theorem. So the rational root theorem states that the possible rational zeros of a polynomial function are of the form p over q, where p and q are the factors of the constant term and the leading coefficient. So meaning p for the factors of the constant term, while q for the factors of the leading term. When we say leading coefficient, rather, so that's the coefficient of the term of highest exponent. In the first example, this is the leading term, and the leading coefficient is 1. For this is the leading coefficient, since the highest exponent belongs to this term. So verify that the rational root theorem works for the polynomial function f of x defined by this. If you remember, we have made use of this as our example in the previous slide, and we worked on the zeros of this. In fact, the zeros of this equals 1, 2, 3, right? And how do we work on the zeros? This theorem will help us. So let's work on the steps. So let's work on the possible values of p, or the values of p rather, the values of q and the values of p of q, which is the possible rational zeros. Okay, so we have the constant term is negative 6, so the possible factors are positive negative 1, positive negative 2, positive negative 3, and positive negative 6. For q, since the coefficient is just 1, so the possible factors are positive negative 1. Now, since q equals positive negative 1, we can say that the possible rational zeros are the values of p, positive negative 1, 2, 3, and 6, which is true because, again, the zeros of this function equals 1, 2, 3. So if we do not know yet what are the zeros of this polynomial function, and we know the rational root theorem, so we only have these options as regards to working on the possible rational zeros. Okay, so in the previous slide, I've just selected 1 without knowing why we selected 1. And then since we have this rational root theorem, I selected 1 because 1 is a possible rational zero in relation to the definition of the rational root theorem. Okay, for number 2, we're going to work on the value of P and the values of Q as well as P over Q. So here, the constant term is -10. So this is positive -1, positive -2, positive -5, and positive -10. And then for the possible value of Q, because we have the leading coefficient 6, so this is positive -1, positive -2, positive -3, and positive -6. For P over Q, so this is P over 1 here. So we have P, meaning P equals positive -1, positive -2, 5, 10. And then the other is positive -1 over 2. Okay, positive -2 over 2, which is equal to 1. So nandito siya with P. And then positive -5 halves. Positive -10 halves, which is in P also. And then we'll proceed with 3. So positive -1 over 3. Positive -2 over 3, or 2/3. Positive -5/3. Positive -10/3. Of course, we include positive -1 over 6, positive -2 over 6, which is 1/3, positive -5 over 6, positive 10 over 6, positive -10 over 6, which is equal to 5/3 also. So these are your P over Q, or the possible rational roots. Now, in identifying the possible rational zeros for number 2, these are just our selection. So you don't need to consider the set of all real numbers for you to find out the zeros. So your choices will now then be narrowed down to this P over Q, and that's the purpose of the rational root theorem. Now, I want you to, in not more than 3 sentences, I'd like you to summarize our lesson for today and write your summary in the comment box section of this lecture video. Okay, so bye for now.